before I have my baby. So after this unit, I think I can't say his name, Cicerone, some Italian dude that was down here. Sometimes he subs for Mr. Konjak. So far, he's the one that's going to be coming in, but he will be using all of my material. So it's not like he's going to be creating things. You're still going to get the same note packets. You're still going to have the same setup. He's just going to be the one in here. I will be back, though, the beginning of March. Okay, so I'm not gone the rest of the year. I'll be back beginning of March, and that leaves us with 2.5-ish solid months before the AP test together. If for some reason you are struggling while I'm gone, please email me, okay? I know I'm going to be having a newborn, but they sleep most of the time. So you can email me, and I'll try to help you out as much as I can. I'm going to try to take my little camera thing home, so if I can make video lessons, kind of like, you know, how I upload online from here, I'll try to do that if that'll help, okay? So I'm going to try to do my best while I'm not here. Is that okay? I hope you appreciate that, because I would if I was in your shoes, okay? But on a sadder note, this is probably the last thing we're going to cover together, okay? But it's one of my favorites, so that's exciting. All right, so in this section, we're going to cover something called the derivative of a product, okay? Without getting too creative, we're going to discuss the product rule of differentiation, aka finding a derivative. Before we get there, though, we're going to do derivatives our old ways, okay, using our power rule. So at the top, it says to rewrite the function as a cubic function. Do we realize if we were to take a linear equation times a quadratic equation, that would give us cubic, right? A degree of 1 times a degree of 2 would give us a degree of 3. You add the powers. So let's go ahead and distribute through those parentheses, get rid of the parentheses essentially, turn it into, bless you, a cubic function. I know we all distribute in differently, but we should all get the same terms in the end. All right, can we get that cubic? Okay, then find f prime, which means f prime. What does that symbolize? Derivative, okay? So let's go ahead and use our power rule shortcut. I think we're getting pretty good at these. We would have 6x squared minus 14x plus 8. So that's one derivative shortcut we've discussed. What does this equation represent? This 6x squared minus 14x plus 8, what on earth does that mean? Or if we were to use it somehow, what would our answer represent? What do you think, Stevie?
Slope of a tangent line.
It's a slope of a tangent line, okay? So this is an equation that can be used to find the slope of a tangent line at any point on f of x, okay, the original graph that you start. So no matter what x value or what spot you want to check, okay, you're focusing on, you can plug it into this equation because that equation represents the derivative, aka slope of tangent line. Okay, nothing new. For our history buffs in here, though, there is kind of some controversy over calculus and who discovered it. I'm sure you guys have heard of Isaac Newton before, right? Okay, but there was this other dude called Gottfried Leibniz, really crazy looking dude or character. If you Googled him, he has like that French style haircut with all the curls. You know what I mean? Really weird haircut. So what was going on, interestingly enough, is these two gentlemen created calculus at the same time, but without even knowing it. Can you imagine or fathom like how rare that is to create something that someone else is doing at the exact same time? Okay, kind of interesting. Now, Isaac Newton, though, do we know where he was from? What country? England. Okay, Leibniz, can you think about where he's from based off the last name? Germany, yeah, okay. So two different countries, two different men creating calculus at the exact same time, but they had no idea. So the controversy comes into play if they created it kind of at the same time, who can we credit as the father of calculus? So of course England wants Newton to be the father of calculus, and Germany wants Leibniz. Now here's what's interesting. I believe, and I always get these confused, Newton technically created calculus first, or at least he started his work first, but you weren't really considered a creator or developer until you published your work, like in a newspaper or as an article in a book. Leibniz, on the other hand, started his work after Newton, but he published his work before Newton did. Can you see where that's the controversy? So Newton started it first, but he never published it, so it was kind of never official. But Leibniz started his after Newton, but published first, so he kind of beat Newton to the punchline. So there's this big controversy over who is actually the father or developer of calculus. Now, what's difficult, I don't want to say difficult, what is different with calculus than any other kind of subject is because since we have technically these two creators, we have merged or have kind of accustomed ourselves to their two different notations, okay, symbols they use to represent different things. So I'm going to go over those two in this idea. Newton used the notation f prime of x to denote a derivative. Okay, that's what we're used to using so far. That's what we've seen. Leibniz, on the other hand, used something that looks like dy over dx. And I'm not sure if you've seen that notation or not, but this is just another symbol that represents a derivative. Okay, and I want to take a second and talk about where this actually comes from. Okay, remember derivative means slope, basic idea, right? Slope of tangent line. How do we calculate the slope of a tangent line? Or sorry, how do we normally calculate slope in general? Maybe between 2 points, like back to Algebra 1 days. If you have 2 points, how can you find the slope? Little formula, yeah. Minus x1. Okay, basic idea of slope, right? But with a derivative, we want that one x value or 1 point to come closer to the other point. We want the secant line to become the tangent line. We talked about that concept. This same idea, represented in perhaps a science class, might look like this. Have you seen those triangles before? Maybe? Do we know what that triangle means? Yeah, I heard it. Yeah?
Changing.
A change in. Okay, so we have some change in y, over some change in x. That's basically what this is saying, right? If you subtract two things, aren't you finding the difference or the change between those numbers? Okay, so these three ideas, m, y2 minus 1 over x2 minus x1, delta y over delta x, okay, that's what the triangle means. They all mean the same thing. So in calculus, Leibniz used dy over dx, another way to symbolize slope. Do you kind of see how all of those are technically related to each other? You see how all the y terms are up top and all the x terms are on the bottom? Okay, so this notation that we're eventually going to get to this year is just another way to symbolize slope, if you were to see that kind of in the future. Okay, but this came from Leibniz, and what we've been using was Newton's symbol. Okay, so let's go ahead and talk about the product rule shortcut, and then we're going to take an example or a look at that. You actually did this on your test. Do you guys remember the last free response question? Remember multiplying two things together? We did very well on that question, by the way. I was pleasantly surprised. If we have two functions being multiplied together, like f of x times g of x, we have some way to figure out what the derivative would be of those two functions being multiplied together. Okay. Now, on the test, if we can think about it, maybe it's fresh in our minds, what was her name? Lexi, Lily, Lindsay, Lillian, something like that. What did she think the derivative of two things being multiplied together was? But it actually wasn't. Yeah?
F prime of x times g prime of x.
Okay, so intuitively, you guys might think that the derivative of two things being multiplied together is just multiplying the individual derivatives, but you guys saw on the test the other day that this was not the case. Okay, it's not as simple as just finding the individual derivatives and multiplying those together. So there is still some shortcut, it's just not that particular method. Okay, so what we're going to say our power rule shortcut is, we're going to leave the first function the same, but we're going to multiply that by the derivative of the second function. We are then going to add kind of the reverse idea. What if we keep the second function exactly the same, but then we multiply the derivative of the first function? Okay, this is what's called our product rule. When you're multiplying two things together, we're going to see how those derivatives work. Now, my little way of remembering this, not sure if it helps or not, my Calc 2 kids repeat this. I hear them say it when they go through some derivative problems. I say 1 d2 plus 2 d1. So for instance, you keep the first function and then multiply by d2. I'm sorry if that came out a little differently than what was supposed to. I kind of was choking on some mucus. Okay. I saw the laughs. I had to, I'm sorry. That's probably not as bad as what I did my first year teaching. I know. So I was trying to say, and keep in mind, these are like maybe 8th or 9th graders, like kind of exactly. I was trying to say set x equal to 4, and can you imagine what came out instead of set x? Okay. So, I'm not saying it. I'm not going to say it. No. Anyway, okay, our product rule, 1d2 plus 2d1. Okay, keep the first function, multiply it by the derivative of the second, and then you're going to add the second function times d1, the derivative of the first. Okay. When we go through some of these examples, you're going to hear me say 1d2 plus 2d1, and it's going to start to make sense. Okay, so this is our shortcut, another derivative shortcut when we are multiplying two things together, product, meaning multiplication. Okay, so we're going to see why this actually works, or why we have this rule. So to show that it works, we're going to apply the power rule that we rewrote from above. Okay, so we said that, remember these are the two functions we had from the top, right? And didn't we get rid of the parentheses and then find the derivative using our power rule shortcut? Okay, we have that up here at the top. But notice how the way this function initially looks, like we are multiplying two different functions together. Every time I say function, you guys are just going to laugh. Okay, do we realize, I'm going to say piece. Do you realize we have this piece times this one? Okay, so we are technically multiplying two pieces together. So let's see if we apply the product rule, do we get the same derivative from the top? Okay, so let's go ahead and practice this derivative using our product rule shortcut. 1d2 plus 2d1. Okay, which piece represents our first equation? Can you label them? Okay, so our first piece would be 2x minus 3. And then we got to multiply that by d2, the derivative of the second. So what would that look like? Can you use a shortcut there? Good, Braden?
2x minus 2.
2x minus 2. Okay, so that's 1 d2. And now we're going to add 2, the second piece, times d1, the derivative of the first, which is just 2, right? Okay, so that's the initial product rule, 1d2 plus 2d1. Let's simplify it, okay, get rid of some parentheses, to see if it matches the same derivative that we know it should be from the top. Okay, so we have a little distribution FOIL process to do on the first two terms. And then for the last set of parentheses, we can just distribute in the 2. And let's go ahead and combine all the like terms in the end. It should be a plus 6, my bad. Do we get the same derivative? Okay, so you kind of have options here. If you're multiplying two polynomials together, like linears, quadratics, cubics, quartics, quintics, those types of functions, you have options. You can either simplify them first and then use the power rule to find your derivative, or maybe you want to use a derivative first, in this case using a product rule, and then simplifying. You'll still get the same answer in the end. Okay, so polynomials are kind of easy because you have options. What's a little different and why we have the product rule is what if you're not multiplying two polynomials together? For instance, if you look at the bottom page or the bottom half, what if our function was x squared times sine of x? Do you notice how those are not two polynomials being multiplied together? One's a polynomial, that x squared, but the other one's a trig function. So we can't really rewrite this one like we did the last one and then use the power rule. Okay, we have no choice but to use the product rule on this case. So let's go ahead and try this one. It says apply the product rule to find the slope of the normal line. Okay, so that'll come into play in a little bit. And we're looking at x equals pi. Let's just first use the product rule. Okay, so we'll label g prime as our derivative. Can we label the two? I almost said it, the two pieces being multiplied together. X squared, right, is the first equation or piece, and then sine of x would be the second piece. Okay, so going through our product rule, we need 1 d2 plus 2 d1. So we labeled x squared as 1, and then we got to multiply that by d2, the derivative of sine. Cosine, that's another shortcut for us, okay, plus 2, okay, times d1, the derivative of x squared. We got 2x. Okay, now you can leave it like that. I know some of you like to reorder things, so if you do want to move the 2x out front of that sign, you could. You can't multiply the x's though, okay, because the x with the sign is technically inside parentheses. It's being held captive. You can't really do anything with it. So that 2x has no other option than to go out front if you wanted to rewrite it. Okay, so this is our derivative that's representing the slope of the tangent line at any point. How might we use that to help us figure out the slope of the normal line? What's our connection between tangent and normal? They're perpendicular. Okay, so let's go ahead and figure out what the slope of the tangent line is at this spot of pi, and then we'll use that perpendicular slope to help us write the normal slope. So we're going to plug in pi into all of these x's. Alright, so we're using trig. We got to know our unit circle. Pi is one of the ones, the big ones that we have to know. What is cosine of pi? -1. So we have -1. Maybe I'll write that down. We have pi squared times -1. And then what about sine of pi on our unit circle? Pi is our leftmost point. 0, good, okay. So it looks like we're just left with negative pi squared. Okay, but this is what we got when we plugged in pi into the derivative. So this is representing the slope of the tangent line at pi. How can we then represent the slope of the normal line with that perpendicular idea? A little tricky because it's pi. I know it's not exactly a number, a whole number, but it is a number after all. What do you think, Joseph?
1 over pi squared.
1 over pi squared. We need the opposite reciprocal. So if it's negative, we got to change it to positive and reciprocate it. Instead of pi squared, we'd have 1 over pi squared. There's our slope of normal. Okay, so just like all of the other types of questions we've been answering about tangent line slopes, normal line slopes, equations of tangent lines and normal lines, we're still going to be seeing those, which I think we're getting really comfortable with. We're just adding a new derivative shortcut to help us figure out a slope or a derivative. Okay, so that's specifically the product rule. Let's go ahead and try some more of these. Use the product rule to find the derivative. Okay, just practicing this shortcut. If you're going to use a product rule, you seriously have to be multiplying two things together. That's why it's called product. So can you identify, at least in this first one, what two pieces are being multiplied together? Can we label them as 1 and 2? You don't have to write it down, or you got to at least think about it. What represents the first function piece? Bless you. What represents the second piece? All right, let's go ahead and try our product rule. Let's see, we have 1 d2 plus 2 d1. Are we getting used to that? 1d2 plus 2d1? Okay, let's go ahead and clean it up. We're going to get rid of all those parentheses so we have some distribution, foiling, and then we'll eventually combine some like terms. Can we get that derivative? Check it out. Okay. Now you could have approached this the other way we've discussed up to this point using the power rule. If you wanted to initially multiply those two quantities together and then take the derivative, you would have gotten the same thing. Okay, because these are two polynomials being multiplied together. All right, but in some cases, like the one right underneath it, okay, we can't simplify it at all or rewrite it. So we have no choice but to use the product rule. Can we identify what's our first piece and second piece? What are the two things being multiplied together? Are we thinking x cubed is the first and sine is the second? Okay, so let's go ahead and through our product rule. 1d2 plus 2d1. All right, we really don't have any distribution or foiling to do like we had in the last one. The only way you really could rewrite this if you wanted to was move that 3x squared in front of the sign of x. That's another way it might look. Okay, but other than that, that's basically our product rule to give us the derivative. We doing okay? 1d2 plus 2d1. I'm going to burn it into your brain just like point slope form. All right, let's go ahead and try g of x, the corner one that I skipped. Let's go ahead and label the first piece and the second piece, the two items being multiplied together. Again, if you wanted to, you could distribute in the square root of x and then use a power rule, but let's practice our product. Okay, I'm going to erase these little pieces so I have more room here. All right, so 1, we're going to keep the square root of x. Maybe you want to rewrite that. Maybe rewrite it as x to the 1/2 power. We practiced that, right? Rewriting roots as fractional exponents. Okay, so there's 1, and then we got to multiply that by d2 plus 2 times d1. Okay, so if you rewrite the square root of x as x to the 1/2, you can use your power rule. So that would end up being 1/2 x to the negative 1/2. We're going to practice cleaning this one up. Okay, so let's go ahead and distribute in x to the 1/2 power. What do you think we're going to get? X to the 1/2 times 2x. If you multiply the same base, what do you do to the powers? Exponent properties? What are we going to do? You add them, okay? So when we distribute this in, we're going to need an x to the 1/2 times an x to the first. So we're going to add those powers. 1 plus a half is 1.5, but as a fraction, we'll say that's 3/2. And when we distribute in x to the 1/2 into the -3, that's just going to be -3x to the 1/2. That one's pretty simple. For the other pairs that we're going to get rid of the parentheses for, we're going to distribute in the 1/2 x to the -1/2. So the same idea. If you're multiplying the same bases, we're going to add the powers. So we need a 2 plus a -1/2, which would be 1.5 again. Okay, so the power on the x is 1.5, or you can write that as 3/2. If we do the next distribution, we would need a 1 plus a -1/2. So we would have an x to the 1/2 power. Okay. The coefficient, though, would be 3/2. You have 3 times a half. And then the last distribution, 2 times a half is just 1. And there's no x to add a power 2, so it's just going to stay a -1/2. Do we have any like terms? Let's see, we have a 2x to the 3/2 plus a 1/2 x to 3/2. Those are the same powers, right? Same type of x. So we can write that as 2.5, but as a fraction, that'd be 5/2. And we have a -3x to the half minus a 3/2 x to the half. Those are the same types of x's as well. They're both to the 1/2 power. So -3 minus 1.5 is -4.5. But as a fraction, we could say 9/2. We're going to get really good with fractions this year if you haven't noticed. Fractions. And then the last one we have is just x to the -1/2. Can we make that negative exponent positive? What would it look like?
1 over x to the 1/2.
1 over x to the 1/2. Good.
And you could go even further and have it 1 over x to the square root.
Yeah, if you wanted to convert these back to roots, you could do that. Okay? Let's see, you would have 5/2 times
X to power 3.
times the square root of x cubed minus 9/2 square root of x plus 1 over the square root of x. You can turn them back into roots if you wanted to. Okay? A lot of different ways the derivative can be represented. Okay? You just got to be able to recognize or move or convert between those methods. All right? Let's go ahead and try the next one. Yeah?
Why does it have to be specifically 1d2 and 2d1? Because if you have like those two being derivative, like if you were to have, for example, for the first one, instead of having it be
This first
that one is the same and then the second one derivative, couldn't you have the first one derivative and then the second one the same?
Yeah. Okay, so our product rule, if you are, okay, so we have, if our function is multiplying two things together, one way you can represent the derivative is 1d2 plus 2d1. Okay? Now, you could rearrange this because if you think of algebraic properties, I always get them confused. There's like commutative and associative, those ones. You could have 2d1 plus 1d2 because you can switch the order when you're adding. You can also switch the order when you multiply. So you could have d2 times 1 plus d1 times 2.
So just as long as you have one function and then its derivative, and then the other function's derivative, and then the original function.
Exactly. It's a combination of keeping one function the same times the derivative of the other.
Okay. Just making sure.
That's fine.
Because I did it differently, although algebraically
it still happens. Exactly. So it's those associative and commutative properties that allow you to rewrite it those different ways. Okay? All right, let's go ahead and try the next one. Product rule, multiplying two things together. We have 1 and then d2, the derivative of cosine, negative sign, I heard it, plus 2 times d1. Looks like just 3. Okay, so cleaning it up, we're going to distribute in a negative sign. And then our last one, we can move the 3 out front as a coefficient. We're used to seeing it like that anyway. Okay, and we'll leave our derivative like that. Are we doing okay with a shortcut? Product rule. 1d2 plus 2d1. Do you guys want to try the last two on your own? Give them a shot. Okay, for the g of x, actually, this should be theta. All the variables should be the same. But if you don't like those thetas in there, you can think of them as x's. So if you want to write x over those thetas, maybe that would make a little bit more sense to you. All right, let's check out the first one. What you get is let's just do one term at a time. Okay, don't get too far ahead of ourselves. Just work our way through the equation. What's the derivative of 3 theta? Or just 3x, if you want to think about it like that. Just 3, okay? We then have to add the derivative of the next term. Now, if you take a look at that, it's theta times sine of theta, or x times sine of x. Okay, you're multiplying two functions together. So in order to find the derivative of this term, we're going to have to go through that product rule, 1d2 plus 2d1. So we'll keep the first piece, which is theta, times the derivative of the second. The derivative of sine, what'd you guys get? Cosine, okay. So there's 1d2. We now have to add 2d1. What's the derivative of theta? Or what's the derivative of x, whatever variable you want to use? Just 1. Okay, so you can write times 1 there if you want to, but that's not really going to change anything when you multiply by 1. Okay, so it looks like our derivative is simply 3 plus theta times cosine plus sine. Okay, so work your way across the equation. If you ever come to a point where you're multiplying two functions or pieces together, you're going to have to go through that product rule. How about the second one? Any takers? Product rule, you're multiplying sine times cosine. What did your 1d2 plus 2d1 look like? Go to Anastasia.
Sine x times negative sine x plus cosine x times cosine x.
All right, 1d2 plus 2d1. Can we clean it up? Yeah. Okay, so this would be negative sine squared plus cosine squared. Vinny flipped it though, he just reordered it. He put the positive cosine first and the negative sine squared second, either one. Okay, so I'd say both of those are pretty good. How'd you do? Okay. Let's check out a product rule in terms of a question we're already used to answering. Find the equation of a tangent line from this function at this point. What information do you need to know to write the equation of a tangent line? Any line for that matter. A point and a slope. Okay, so maybe we'll write that off to the side. We need a point and a slope. Where does the point come from? Or where does the slope come from? What do we use to help us figure out those two pieces that we have to know? Let's see, we're specifically focusing on this time or t value of pi over 6. So where can we plug in pi over 6 to get a point value? Where can we plug in pi over 6 to get a slope value? What do you think, Braden?
Point plugged into the original function.
Okay.
And for the slope plugged into the derivative.
We're going to plug it into the derivative. Okay, so we already have the original. They give that to us. Let's go ahead and try to figure out the derivative. That way we can get the slope value. Notice that the original equation is multiplying two things together. You have t squared times cosine. So if you're multiplying two things together, you have to use the product rule shortcut to help you figure out the derivative. So let's go through that. We have 1 times d2, the derivative of cosine. We got negative sign. And then we need to add 2 times d1, which would just be 2t. So if we clean it up, we'll have negative t squared sine t plus 2t cosine t. Okay. We'll stop there for today. We'll go ahead and plug in pi over 6 tomorrow into the original and the derivative to get our point and slope, and then we'll go ahead and write our equation, okay? To be continued.